Hi everyone. Just a little bit of background. I'm a third-year student in the robotics program, and I work with the Ford Autonomous Vehicle Lab here at the University of Michigan. And today I'm going to be talking to you about how modeling camera effects and images can improve autonomous vehicle vision. So what are camera effects? We define camera effects as visual distortions in an image that are caused between the interaction of the camera and the environment during image acquisition. So this can manifest as, my laser pointer isn't working yet. Oh, there we go. As blur, over or underexposure, or images where the overall color is shifted towards one side of the spectrum. So in this case, it would be towards red. A good way of thinking about camera effects is if you were to port an image into Photoshop and make some manipulations or add an Instagram filter to an image. So why do we care about camera effects? So let's talk about the very first autonomous vehicle crash that involved a Tesla. What happened is that the car's autopilot was unable to detect a white truck that was cast against a bright sky. And the question we have to ask is, why did the vision system fail in this case? As Tesla's vision system is proprietary, but we do know that they use deep learning. And so when people in computer vision say deep learning, we're talking about neural networks. So at a really high level, neural networks, which this is the symbol for a neural network that I'm going to be using throughout my presentation, neural networks are a series of highly connected but simple processing units. And so usually we define the architecture by different layers, and each layer is a series of nodes that are connected together. So a good example of how we would use one of these is, let's say we want in an image, we have an X, Y, and Z location, and we want to predict if there's a car in that location. So normally in the input layer, we would put in the X, Y, Z, and our output would be a car label. So to understand how each of these nodes processes information, we can say, so each of these connections is assigned a weight value to them. And so what the node does to all of these inputs is it scales the X, Y, and Z values and sums them together. And then this information is passed to all of the nodes that it's connected to in the next layer, and so on and so forth. So at a really high level, what we can think of that neural networks are doing is they take some input X and they learn a mapping function, so like y equals ax plus b, to some sort of output space. And what's really cool about neural networks is that you can take really high dimensional input spaces like images and learn mappings to label spaces through a very complicated function where you have millions of A parameters and millions of B parameters. So the way that we teach neural networks how they learn what this mapping function is we give them a bunch of images and they predict a bunch of outputs, and the A and B coefficients are manipulated based on how good the predictions are, or based on the error. However, what we find is that the function that learns to map between the input and output is dependent upon whatever information exists within the input space. And so let's say in this example, we want to learn this truth, this real world model, y equals ax plus b, from these data points. We see that if the data points are only a small subset of the actual input space, so if they only span a really small part of it, that the neural network, the learned model, won't be representative of what the real world model is. And so if we kind of go back to this idea of the Tesla crash, if a neural network is trained to only find cars and images that have no representation of a camera effect like exposure, there's no guarantee that when a neural network is deployed in this case, that it can reliably detect a vehicle. So this brings us to the question, what is the important visual information that we want our neural networks to be aware of? And so in this image, we have two, what we refer to as benchmark data sets. And by benchmark, it just means that these are kind of the holy grail data sets that we deploy our algorithms on to test how good they are. And so one is called Kitty, and the other is called Cityscapes. Both of them were collected in Germany, probably like during midday, and they're all of different road scenarios. And so in these data sets, what we want represented is a variety of different types of scene structure. So this can be different times of day, different shadows, different types of buildings, different road configurations. And we see that Kitty and Cityscapes are very similar when it comes to these types of visual information. However, where they differ are in the pixel statistics. So you can see that Kitty has much more bright than Cityscapes is. And it also is skewed more towards blue in terms of the overall tone instead of Cityscapes. And so we see that there's this other aspect that we want to pay attention to in our data sets. And so kind of if we think about all of the possible visual factors like scene structure that we want to capture in the real world, that these data sets only get subsets of them. So like Cityscapes might capture a little bit different color profiles than Kitty does. Our truck images get visual factors that are over here. And ultimately what we want to do is to come up with algorithms or data sets that are more representative and capture more of the real world than what we have currently. So why not just capture a bunch of real-world data? I mean, that's what Google does, right, is they just drive cars everywhere. And so in computer vision, we actually do have sort of this giant data set. It's over 20 million images. It took 2 years, a year and a half to collect. It has a bunch of different seasons represented in it, a bunch of different weather conditions, lighting conditions, times of day, and this is it. This is what we want to train our algorithms on. However, to label each one of these algorithms so we know where the cars are would cost about, let's say, $50,000 for 5,000 images. The time to take a human to pick out each car is about 1.5 minutes. And so we see that to label this data set, it would cost over $200 million and take over 300,000 man-hours. So labeling, this is the huge cost that is associated with labeling real-world data, which means that we can't really, collecting large data sets isn't an option for us. So an alternative is to create synthetic data sets. So what's really cool is rendering engines like those that are used in Grand Theft Auto. You immediately get your labels from them. You know where each car pixel exists in the image, and which is awesome because we can create as much labeled data as we want now. And so an example of one of these data sets is where actually it was created based on Kitty. So Kitty was rendered in different scenarios to include more times of day and more weather. And so this is called the virtual Kitty data set. So ideally, if we go back to the real world, ideally what we want is these virtual data sets to capture all of those other visual factors that our real data sets are missing. However, what we find in practice is that they do capture a little bit, since Virtual Kitty is based on Kitty, it captures a little bit of the scene structure that Kitty and Cityscapes has maybe more weather represented, but there's also these really unpleasant rendering artifacts where it doesn't, these synthetic images still don't look real. So what our proposed solution is to model camera effects in these images. And so this is an example of where a neural network is fed an image of a cat, and we make small, different visual distortions to it that are similar to what a camera does, so blur, noise, messing around with the contrast, and JPEG means how an image is stored as a JPEG. And we see that under certain instances that these camera effects really mess up how the neural network performs. And so what my research involves is how do we effectively model these camera distortions in data so neural networks can learn about them. And so things that we do are, as I kind of mentioned before, adding in blur, messing around with the exposure, adding in realistic camera noise, and manipulating the color post-processing, which basically just means like it's kind of like applying the sepia filter in Instagram. And so these are some of the output images that we get, where we've taken images from Virtual Kitty and added these effects into them. And what's really great is that when we train neural networks on our augmented images, we find that we get a significantly higher performance when testing on real-world data, which is really exciting, especially because adding in these effects really takes no cost. You know, we don't have to label or any additional images, which is great. And so right now, our future work is looking at how we can teach neural networks to change these images by themselves. So thank you.